Okay, so this is deMoivre's theorem and a very important application. That's what this section is about. We talked about already how multiplication of complex numbers works really, really well with the trig form of complex numbers. So let me do a quick recap here. So if I have z1 is a complex number, it's r1 cos theta plus theta 1 plus I sine theta 1. If z2 is equal to r2 cos theta 2 plus I sine theta 2, then the product z1, z2 is just r1, r2 cos theta 1 plus theta 2, and then plus I sine theta 1 plus theta 2. All right, so we talked about this last time, and essentially this result comes from the fact that we have our identities for breaking down cosine theta 1 and theta 2 plus theta 2, and breaking down sine theta 1 plus sine theta 2. And those identities essentially immediately give you that z1, z2. When you FOIL these two expressions, when you multiply these two expressions out, you get exactly the two guys that we see here. Okay, so again, the conclusion was that multiplication of complex numbers, when you do multiplication of complex numbers, is very profitable to think of them in terms of their trig forms. All right. So of course we had the same similar result with division, right? z1 over z2 would have been r1 over r2 cosine of theta 1 minus theta 2 this time, and then plus I sine theta 1 minus theta 2. All right. So this was very nice in terms of kind of the computational aspect of products and quotients of complex numbers. But remember also there was very nice geometric interpretations where what you're doing in terms of the angle at least is if you have the product of two complex numbers, the first complex number has angle theta 1 with the x-axis, the other has theta 2 at the x-axis, right? Their product is going to have angle theta 1 plus theta 2 with the x-axis. So when you multiply complex numbers, you're in a way adding their angles. And when you're dividing complex numbers, you're subtracting their angles, right? Of course, their lengths in the multiplication case multiply, and their lengths divide when you take the quotient. All right, but it's this sum of angles and subtraction of angles that's really interesting when it comes to the product and quotient of complex numbers. So what we're going to talk about today is what about powers? So what about powers? Right? So powers essentially, right, are multiplication, right? So when you think of z1 squared, or let me just say z squared, right? Sorry, let me actually write down just the baseline. Z equals r cos theta plus I sine theta, right? If I look at z squared, what is that? That's just z times z, right? So powers essentially are like multiplication, right? So I say essentially, I say like multiplication because of course you can have powers which are not quite exactly just multiplication, right? Z to the 1/2, z to the -3, stuff like that, right? Z to the 0. These guys aren't really multiplication, but because in a way the kind of core idea behind powers is multiplication, z squared is z times z, what we expect is the trig form. When we work in trig form with powers, we expect something nice and simple, right? Just like in trig form, multiplication is nice and simple, all right? And in fact, it turns out to be exactly nice and simple because, well, for this one example up here, z squared equals z times z, we can just use deMoivre's theorem. We can just use the product that we talked about above, the property, right? Z times z would be in trig form r times r, which is r squared, and then cosine of theta plus theta, right? Because we're multiplying the same thing, z times z, right? And then plus I sine of theta plus theta, right? But theta plus theta is just 2 theta. So this is r squared cosine of 2 theta plus I sine of 2 theta. Okay. All right, so what we see here is when I square my complex number, in terms of trig form, what happens is the magnitude or length or distance to the origin of my complex number is squared, right? Remember, the r is the distance to the origin. So if we draw the complex number, so this one right here, r cos theta, I sine theta, this angle is my theta, and r represents that distance right there, distance to the origin, right? So if we square our complex number, the distance to the origin is squared. And sorry, that looks really messy. And the angle is doubled. All right. Okay. So let's extend that one more time. Let me work on these three guys. Let me talk about these three guys in a couple seconds. But what about z cubed? Well, z cubed is z squared times z. I want to write it like this because I just figured out z squared, right? And so what is that? That's r squared cos 2 theta plus I sine 2 theta times r cos theta plus I sine theta, right? Z squared times z. And then again, using what we learned last time from properties of multiplication, right, in terms of trig form, this is going to be, sorry, I didn't even have to write that out, I guess. Yeah, let me just, sorry. No, this is okay, sorry. This is cosine 2 theta plus theta, and then plus I sine 2 theta plus theta. This is from last week, right? Or last time. Right, and that's r cubed cosine 3 theta plus I sine 3 theta. And now we can see the pattern, right? When I cube my complex number, the distance to the origin cubes, and my angle triples. My angle triples, right? Before, when it was squared, my angle doubled, my angle doubled. And of course, we can certainly believe at this point r to the 17, sorry, z to the 17. What's going to happen is we're going to get r to the 17 cosine of 17 theta plus I sine of 17 theta. Okay, so the angle would multiply by a factor of 17. Our distance to the origin would multiply by a would be a power of 17. Okay, so this is the essence of deMoivre's theorem. Oops. It says that when you take any power, let me just use n for the power, then you get r to the n cosine n theta plus I sine n theta. All right. So our pattern that we just talked about works, and this is actually true for n equals anything. Let me put that in quotes here. So what I mean is you can have n equals a half is okay. N equals 0 is okay. All right. N equals -1 is okay. All right. So it works not just for whole numbers, positive whole numbers, as we've just talked about. It works for anything. All right. And you can actually kind of understand these other ones through the understanding of all the ones that we just talked about. But I think maybe we don't really need to talk about that for our class, because for our class, we're mostly focused on, at least certainly for this section, z to the n, where n is a whole number, positive whole number. Okay. But again, this entire discussion, this entire idea of taking powers and having that correspond to kind of rotating or doubling or halving your angle still works. Okay. So in particular, z to the 1/2 would be r to the 1/2 cosine of 1/2 theta plus I sine of 1/2 theta. All right. So what that means is your angle before was theta, now it's half theta. All right. So you're in a way rotating backwards by a factor of a half. All right. Okay. So in terms of the picture, right, we think of, especially if you have a whole number, positive whole number power, what you're doing is you start with your angle theta, and then if you cube it, you're doing 3 of these angles, right? You're rotating 3 times, right? If you're taking to 4th power, you're doing it 4 times, and so on. All right. So again, it relates to kind of rotational motion, and that's where you see a lot of the applications where you actually use this kind of property. All right. But what we're going to use this theorem, this deMoivre's theorem for, is for solving powers. Actually, sorry. Before I even talk about that, let me talk about the zero case, because that's kind of interesting, right? Z to the 0, that's r to the 0 cosine of 0 times theta plus I sine of 0 times theta, right? Well, anything to the 0 should be 1, right? So if everything is consistent, which of course it is, this guy should be 1, and that right-hand side should be 1 as well. So let's just make a quick check to see that, in a way, mathematics isn't crazy, that everything is consistent. So this r to the 0 is 1, because anything to the 0 is 1. Cosine of 0 times theta is same as cosine of 0, but cosine of 0 is 1. Sine of 0 times theta is sine of 0, but sine of 0 is 0. So altogether, this right-hand side is equal to 1 times 1 plus 0i. 1 times 1 plus 0i, which is just 1, right? Which is, of course, what you expect. So, of course, everything is consistent, all right? All right, it's always good to kind of check these for a few simple examples to see if everything, in a way, makes sense. All right, in any case, let's get to kind of the meat of this section, which is the application of deMoivre's theorem, which is solving powers. So let's solve z cubed equals 125. All right. So this is, we're talking about complex numbers here. And the deal is with complex numbers, there's going to be 3 solutions. All right. So when you have complex numbers and you have a problem that has a power like this, a polynomial problem that has a power, the biggest power here, that's how many solutions there's going to be. All right. So if I have z to the 4th plus 3z squared plus 4z minus 1 equals 0, you expect 4 solutions. All right. All right, so we expect 3 solutions here. Sorry, we expect 4 solutions, but some of them might be counted as double. For example, if I have x minus 1, just like in this way, x minus 1 squared equals 0. When I solve this, this is actually x minus 1 times x minus 1. So x equals 1 is kind of like a double solution, so that would count twice. So if you do count things twice, anytime you have a power here, the biggest power, if it's 4, there's 4 solutions. All right. So here, in our problem that we're looking at right now, there's actually going to be 3 solutions. All right. Notice with real numbers, there's only 1 solution. That would be 5. 5 cubed is 125, but that's the only thing. But now, since we're in the realm of complex numbers, there's going to be 3. All right. And again, it seems weird, why would you care? But again, when you talk about rotational motion, you're kind of asking here, what thing cubed is 125? That's the same as asking what thing, if you rotate it 3 times, gets you to here, right? Because 125 on the in the complex plane, when I draw it, it lives here, right? It's on the x-axis because it's a real number. The I component is 0, so it's the position is 125 comma 0, right? So I'm asking which complex numbers, when I rotate them 3 times, because I'm cubing it, gets you to here. All right. So this is very relevant when you're working with rotational motion, or any sort of. So I've been focusing on rotational motion because it's very approachable. But anytime you have oscillatory motion, something that moves back and forth, like a spring or a pendulum, those are very, very nicely described by complex numbers as well, because of the sines and cosines. Exactly. Because sines and cosines oscillate, right? They look like this, up and down, up and down, up and down. And so oscillatory motion actually is where the really, really important applications are. And again, those you have to work with complex numbers, and then that's where problems like this might arise. Okay, so let me write this problem in words. So I can also phrase this in words as find the cube roots of 125. All right. And again, I'm in the realm of complex numbers. Maybe just to emphasize, I'll stick in the word complex. Just to emphasize, we're not just talking about the real numbers, but also complex. All right, so how would you solve this? So the way we do this is we're going to work in trig form. All right. So in trig form, let me write each of both. So I want to work in trig form, so I want to write both of these guys in trig form. All right. So 125, I'm going to write this in trig form. 125 is equal to, well, 125 lives right there on the x-axis. So its angle with the x-axis is 0. And so I know the angle portion is 0, and its distance to the origin is 125. So this is 125 cosine of 0, and then plus I sine of 0. All right. All right. What about z? So let me give z a name as well. And what I'm going to do here is I'm not going to use r and theta, because later we're going to use r and thetas for the right-hand sides a lot. So I want to use something different in order to not get confused. So I'm going to use s and alpha. It follows the notation in the book as well. So s cosine alpha plus I sine alpha. All right, in place of r and theta. Okay, so if 125 is this and z is this, what we're looking for is we want z cubed equals 125. So writing this in trig form, that's equivalent to s cos alpha plus I sine alpha cubed equals 125 cosine of 0 plus I sine of 0. All right. Okay, this is just a rephrasing of our problem. But here's where we use deMoivre's theorem. When you cube a complex number, right, we know that the distance to the origin, s, is cubed, so s cubed. And then the angle is tripled. So this is cosine of 3 alpha plus I sine of 3 alpha. All right, the right-hand side, we just leave it, 125, cosine of 0 plus I sine of 0. All right. Okay, so now we just match terms. S cubed, the distance to the origins have to match. S cubed should be 125. All right, and here remember, S is these distance to the origins, right, are actual distances, right? So so they're real numbers, right? So S cubed equals 125. That means S is equal to cube root of 125, just a regular real number, right? And so this is going to be 5. Okay. So immediately we have S. S is 5. So S equals 5. Okay. So all we have to do now is figure out theta, and we're all set, right? So this is actually, in a way, why we learned the section about solving for solving sines and cosines. Right? When is cosine of 3 alpha equals to cosine of 0? Right? So let me first write some words. Need cosine 3 alpha equals cosine of 0. Right? And of course we need sine of 3 alpha equals sine of 0. Right? So when we have it written like this, well, 3 alpha can be 0. Right? That works. But of course there's more solutions because we know sine and cosines are oscillatory. And we know that that means 3 alpha is 0 plus 2 pi k, right? Where k can be any integer, right? K could be 0, plus or minus 1, plus or minus 2, and so on. Right? So there's actually an infinite number of solutions to this problem. And in general, that means alpha is equal to, that 0 just goes away, right? So 2 pi k over 3. K equals, again, 0, plus or minus 1, plus or minus 2, and so on. All right. So first of all, it seems like there's an infinite number of solutions, but let's actually examine them, right? So let's look at, let's write them down. So let's start with 0. K equals 0. That would correspond to the solution alpha equals 0. All right. So that gives me one solution to my problem. Okay. This solution would be S was 5. So we have it up here. S is 5, alpha is 0. So that would give me Z is equal to 5. How should I write this? Let me write it in full trig form. So this is cosine of 0 plus I sine of 0. All right. I'm going to draw all these later as well because that's going to be really illuminating. Okay, K equals 1. That's alpha equals, K is 1, 2 pi over 3. All right, so that means Z equals 5 cosine 2 pi over 3 plus I sine 2 pi over 3. Okay, k equals 2 gives me alpha equals 4 pi over 3, right? Because k equals 2, I get 2 times 2 is 4. So z is equal to 5 cosine 4 pi over 3 plus I sine 2 pi over 3. All right, and here's where it gets interesting. K equals 3 gives me alpha equals, when k is equal to 3, this 3 on top and the bottom cancel, right? Let me actually write this out. 2 pi, 3 over 3. So I just get 2 pi. Okay. And so what I get is z equals 5 cosine of 2 pi plus I sine of 2 pi. Right? But remember, of course, cosine and sine are periodic with period 2 pi. So cosine 2 pi is the same as cosine 0. And sine of 2 pi is the same as sine of 0. So if I actually compute this, right, cosine 0 is let me write over here, cosine 0 is actually 1, sine of 0 is 0, cosine of 2 pi is 1, is the same thing, sine of 0 is 0. So this k equals 0 solution is z equals 5. K equals 3 solution is also z equals 5. So k equals 3 is actually not a new solution, right? So even though it looks like there's an infinite number of solutions, what's going to happen is most of them repeat, right? K equals 3 is the same as k equals 1, right? So this is same as k equals 1. Oh, sorry, k equals 0, right? So let me just cross that out to indicate, it's one that we already have. Okay, let's look at k equals 4. What's going to happen is that means alpha is equal to 2 pi times 4 over 3. Okay? But I can think of this as 2 pi times, let me write it like this. 1 plus 3 over 3. And that's 2 pi over 3 plus 2 pi times 3 over 3. Right? Those 3's cancel, so I get 2 pi over 3 plus 2 pi. All right? So what happens is that corresponds to z equals 5 times cosine of 2 pi over 3 plus 2 pi, and then I sine of 2 pi over 3 plus 2 pi. All right? But again, sine and cosine are both periodic with period 2 pi. So this cosine of 2 pi over 3, right, that's literally the same as cosine of 2 pi. Sorry, this cosine of 2 pi over 3 plus 2 pi is the same as cosine of 2 pi over 3. The sine of 2 pi over 3 is the same as sine of 2 pi. Sorry, sine of 2 pi over 3 plus 2 pi is the same as sine of 2 pi over 3. All right? And of course, that's the same as the k equals 1 solution, right? We can literally see that they match perfectly. And so this guy here is same as k equals 1. Right? So we actually already have this solution as the k equals 1 solution. Right? So again, these guys are going to repeat quite a bit. And of course, probably a good exercise for you is to see k equals 5. And what's going to turn out is same, if you do exactly the same kind of analysis, this is the same as k equals 2. All right? And then it's just going to keep repeating in the same way. So k equals 6 is going to be same as k equals 0. So it's just going to repeat 0, 1, 2, and then the next 3 are going to be the same as 0, 1, 2, and the next 3 are going to be the same as 0, 1, 2, and so on. And this is also the case for the negative ones as well, for the negative k's. All right. So in essence, what looks like an infinite number of solutions, when you actually write them out as z equals blah, 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 and you actually compute the cosines and the sines, you're only going to have 3 different ones. All right. So ultimately, the way we generally write these solutions is, at least for this particular example, is we have z is equal to, s was 5, and then we're going to write cosine of, and then the angle is going to be 2 pi k over 3 plus I sine 2 pi k over 3, but not k equals 0, 1, 2, and so on. We're just going to write k equals 0, 1, 2, because there's actually only 3 of them, right? There's no need to write any more because they're all repeating, they all repeat one of the previous ones, all right? Okay, notice one interesting feature here. This 2 is 1 minus the 3, which is the power that we were looking at, right? We were solving z cubed equals 125. That 3 made this guy a 2 here, right? It made it so that it repeats every 3 from 0, 1, 2, and then it repeats starting from 3 and so on, right? So this number here is probably best thought of as 3 minus 1, okay? All right, so in this way, we actually get all the third roots, all the cube roots of 125. So all the numbers, all the complex numbers that when you cube that complex number, you get the output 125. All right. Let's actually write out what those are and then draw the picture because that's going to be really, really nice. So again, let me go back up here. My solutions were the k equals 0 solution. We already figured this out. This one was 5. Okay. The k equals 1 solution was 5 times cosine 2 pi over 3 plus I sine 2 pi over 3. Okay. What is cosine of 2 pi over 3? Well, let's look at our graphs, and also let's do the same for sine, right? Cosine, no, actually, I don't want to compute them. I actually just want to draw them. Sorry, I forgot about that already. Z equals 5 cosine 4 pi over 3 plus I sine 4 pi over 3. Let me draw them. So Z equals 5, right? This was k equals 0, which was the angle 0. So z equals 5 lives right there. All right, so this was my first solution to the problem. Okay, the other two solutions all live a distance of 5 from the origin. That's what that 5 means. So they all live on this circle here of radius 5 about the origin. All right, so the other two also live on a circle of radius 5. Okay, what is cosine 2 pi over 3? That's 1/3 of the way around a full circle, right? Because 2 pi is a full circle. I'm dividing by 3, so that's 1/3 of the way around a full circle, right? If you really like degrees, right, that would be 360 degrees over 3, right? So it's 120 degrees, all right? So no matter how you think of this, 120 degrees or 2 pi over 3, 1/3 of the way around a circle, that's going to be right there, all right? Oops, that's going to be right there. All right. So this is my k. Let me write it like this. This is my k equals 1 solution. This one here is my k equals 2 solution. All right. Okay, what about the next one? The next one is 4 pi over 3. But what's 4 pi over 3? So 4 pi over 3 is 2 times 2 pi over 3, right? 2 pi over 3 was going around from here to there, right? 120 degrees. And then now 2 of them, so I'm going around 120 degrees and another 120 degrees, all right? So another 120 degrees. That gives me k equals, that's k equals 0. That's k equals 1. And this one is k equals 2. All right? So this one is 120 and then another 120 gives me 4 pi over 3. All right? So my 3 solutions actually have this nice symmetry. Here, 120 degrees, 120 degrees, and then what's left to get back here, it's another 120 degrees. Okay? Or 2 pi over 3, right? 2 pi over 3, 2 pi over 3, 2 pi over 3. So there's this really nice symmetry. Every 120 degrees, starting from 5 here, I get a solution. All right? So what happens is, in terms of the repeating solutions, k equals 0 was this one. K equals 1 was this one. K equals 2 was this one. K equals 3 would be a rotation of another 120 degrees. That would be back here. K equals 4 would be a rotation of another 120. That would be here. K equals 5. K equals 6 comes back. So every time you rotate 120 degrees, that's giving you another solution. But of course, because you're repeating a lot, there's actually only 3. All right. Okay. So very symmetric, right? Very symmetric. The picture of these solutions. Right, and of course, if you actually wanted the coordinates, the a plus bi of the standard form of each of these solutions, all you have to do is calculate cosine of 2 pi over 3, sine of 2 pi over 3, and that would give you this coordinate right there, right? Calculate cosine 4 pi over 3, calculate sine of 4 pi over 3, that would give you that that one right there in terms of standard form and so on. All right. But generally, we can just leave them like this. All right. So this is solving for these roots. In this case, the cube root of 5. We can do this with solving any. All right. So this is 6.3. A couple more examples, because in the main video, 2 examples didn't get recorded for some reason. So let me redo them. So the first example is we're solving for z to the 4 is equal to 1. So this is another way to say this is solve for the 4th roots of 1, or solve for the 4th roots of unity. So unity means 1. Let me write that more. Unity. All right, so 4th roots of unity. The roots of unity are actually really important. So if you want z to the 5 equals 1, those would be a 5th roots of unity. Z equals 10, z to the 10 equals 1, that would be the 10th roots of unity, and so on. All right, so these are roots of unity because, for example, if you're solving for x squared is equal to 4, right, you're solving for the root of 4, right? You're solving for x equals square root of 4, which is 2, right? So we're solving for the roots of unity. Okay, so we do this example just in the same way as we did before. So this is 1. We write everything in trig form. So z is equal to, and again, we're following the book's notation here. So we're using s and alpha, I sine of alpha. And 1 is equal to, so we transform this into trigonometric form. And this one we don't really have to do any work because 1 lives right there, right? It's on the x-axis in terms of the complex plane. So the angle that 1 makes with the x-axis is 0. Its distance to the origin is 0, right? Its absolute value is, its distance to the origin is 1, right? So its absolute value is 1. So it's just going to be cosine 1 times cosine of 0 degrees or 0 radians, doesn't matter, I sine of 0. All right. Okay, so that means solving z to the 4th equals 1 is the same as solving s cos alpha plus I sine alpha, all to the 4th, is equal to 1. But using deMoivre's theorem, this is s to the 4th cosine 4 alpha plus I sine 4 alpha equals 1. All right. I should be writing trig form here, cos 0 plus I sine 0, just so that we can match these things easier. Cos 0 plus I sine 0. All right. Okay, now, immediately, s to the 4th, the coefficient in front of this cos 0, I sine 0 is 1. So immediately s to the 4th is equal to 1, which means s is equal to 1. All right. There's actually another solution, s equals minus 1 as well. But that's going to be covered by our alphas. All right. So we'll get, actually, no. We don't want s equals negative 1 anyway. Sorry about that. Because we want s to be a positive number, right? Because s is supposed to represent the distance to the origin. All right. We're not, for our class, we're not, at least right now, we're not thinking about having negative s's at the moment. All right. Later on, we will kind of, in a way, when we talk about polar coordinates. But for now, only positive. So s equals 1 is the only solution. All right. Sorry about that. So now we have to match the cosine 4 alpha to the cosine 0, and then the sine 4 alpha to the sine of 0, right? So 4 alpha has to be 0, and then plus 2 pi k, right? And potentially, there's always a second solution, but in this circumstance, right, cosine 4 alpha equals cosine 0 is cosine 4 alpha equals 1. But when is cosine equal to 1? It's only at 0 and then every 2 pi. Okay? If there were two solutions, what would happen is you would have to write them both down, and then you would have to check with the sign for alpha equals sine 0, which one of the two that we actually want, right? And it's going to always turn out that it's always going to be the in a way the obvious one in a way. Okay. So for alpha is going to be equal to 0 plus 2 pi k. And again, if we just plug it into here, into the sine for alpha, sine of 2 pi k is actually equal to 0. So this is just simplifying this. This is just 2 pi k. All right. And so, of course, alpha is equal to 2 pi k over 4. All right. So that tells me my solutions are going to look like s is equal to 1. So it's cosine 2 pi k over 4. And then plus, just cosine 2 pi k over 4, plus I sine 2 pi k over 4. And what is k? K can be 0, plus or minus 1, plus or minus 2, and so on. All right, so k equals 0, plus or minus 1, plus or minus 2, and so on. All right. However, so let me write z equals. However, what's going to happen, again, is many of these are repeats, because we're actually taking cosine of the 2 pi k over 4 and sine of 2 pi k over 4. So every time we repeat, we because of the periodicity of sine and cosine, a lot of the repeats will, a lot of these guys will repeat, and there'll only be a few actual solutions, right? Let's write them out again. K equals 0 tells me alpha is 2 pi 0 over 4, so it's just 0. K equals 1, alpha equals 2 pi over 4, which is pi over 2. K equals 2 gives me alpha equals 2 pi times 2 over 4, which is just pi. K equals 3 gives me alpha equals 2 pi times 3 over 4, which is 3 pi over 2. All right. And then now what's going to happen is k equals 4 gives me alpha equals 2 pi times 4 over 4, which is 2 pi. Right? But when I take cosine of 2 pi, that's going to be the same as cosine of 0. When I take sine of 2 pi, that's going to be the same as sine of 0. So this solution here, k equals 4 solution, is going to be the same as that solution right there. Right? And again, if you do k equals 5, you're going to get the same exact idea. Alpha is going to turn out to be pi over 2 plus 2 pi. And so when you plug that into your sines and cosines, that one's going to be the same as this solution. Right? So all the rest of them are going to repeat, and even if you did the negative ones, you can try them out, they're going to repeat as well. Right? So there's actually only 4 fundamental solutions. The k equals 0 to the k equals 3 solution are all different, but all the others repeat. All right? So let me kind of just cross them out. Right? We only obviously want to write down the ones that are different from each other. So ultimately, what happens is we have 4 solutions, and let me actually plot them again, just as with the previous example. Alpha equals 0 means the angle with the x-axis is 0, so it lives right there, right? Its distance from the origin is 1. All of these distance to the origin is 1 because s was equal to 1 up here. All right, so this one is the first one, k equals 0. Let me label that, k equals 0 solution. The next solution is at pi over 2, which is 90 degrees, which is right there, right? So this is k equals 1. The next one is at pi, which is 180 degrees, right there. This is k equals 2. And then the next one is at 3 pi over 2, which is right there, 270 degrees, k equals 3. All right, and if we did k equals 4, it would come back to the k equals 0, 1. That's exactly what's going on with these computations. K equals 4, k equals 5 would be actually the k equals 1, 1. All right, so what you can see is every pi over 2, right, we get another one. K equals 0, and then pi over 2, right there. 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 All right, and what's significant about pi over 2? Well, pi over 2 is the full circle divided by 4, right? What's significant about 4? We're searching for the 4th root of unity. We're trying to solve z to the 4, we're trying to solve z to the 4 is equal to 1, right? So the solutions are all 2 pi over 4, which happens to be pi over 2, rotation from each other. Oops. Right? So we have this really, really nice symmetry in terms of the solutions. We have the k equals 1 solution, and then every pi over 2, every 90 degrees, we get another one. And again, why 90 degrees? Because 90 degrees is 360 degrees divided by 4. And why 4? Because we're solving z to the 4 equals 1. All right. By the way, all of these 4 solutions make sense, right? If you write these k equals 0, 1, 2, 3 solutions in trig form, you'll see that you get, this is 1, this one is I, minus 1. You don't even have to write it in trig form to see this, of course, because the coordinates here is 1, 0, so that 0, 1, so that represents I. The coordinates here is minus 1, 0, that represents negative 1. And the coordinates here is 0, minus 1, so that represents minus I. All right, so that's an alternate way to see the same thing. So all of these 4 actually make sense, right? 1 to the 4 is obviously 1. I to the 4 is 1. We talked about that. It was very important in terms of calculating powers of I. Minus 1 to the 4th is obviously 1. And minus I to the 4th is 1 because I to the 4th is 1, right? And then the minus sign gets absorbed by the 4th power. All right, so of course all our solutions make sense. All right, so let me just write the solutions kind of as clearly as possible. So solutions are z equals 1, I, minus 1, and minus I. All right. Okay, but it's the symmetry that's really interesting because in a way, let's say I want to calculate the 6th roots of unity, right? So solve this, which is again equivalent to find 6th roots of unity. All right. Immediately, actually, I mean, I could go through the same exact procedure I just went through for z to the 4 equals 1. But, you know, the symmetry idea tells me my solution, I'm going to have one solution at 1, because 1 to the 6 is 1. And then every 2 pi over 6 angle, I'm going to have another solution. All right. So every 2 pi over 6, which is pi over 3, I'm going to have another solution. Or another way to say this is 60 degrees. Every 60 degrees, I'm going to have another solution. All right. So if I rotate 60 degrees, I'm going to get a second solution. If I rotate another 60 degrees, I'm going to get my another solution. Right. So this would be another 60 degrees. So this one would be at a total of 120 degrees. If I rotate another 60 degrees, I get another solution, and this one happens to be right there. Right, negative 1, because negative 1 to the 6 is also equal to 1. If I rotate another 60 degrees, I'm going to get another one. Oops, sorry, this one, maybe I draw this one more accurately. So another 60 degrees. Going to get another one, 60 degrees. So 1, 2, 3, 4. Yeah, right there. And then another 60 degrees. I get my 6th one, and if I do more, I just come back to where I started, right? So my 6th roots of unity are going to live here, 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 and here, and here. And so you can see this actually nice symmetry again, right? This is a little messy. Let me write them just by themselves. Here, 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 and here. All right, so we have this really nice symmetry right there. All right. Okay, and again, the 60 degrees comes from dividing our full circle, 2 pi, by 6, right? Or if you want to just work in degrees, 360 divided by 6 is 60 degrees. Right? So again, this emphasizes how simple calculating roots of unities or roots are when we were working with trig form. All right, imagine how difficult it would be to do this in standard form, right? A plus bi to the 6 is equal to 1. How would you solve that? You would have to multiply this out, right? And then try to figure out what a and b are, right? So if I multiply this out, I would get something like a to the 6 plus a to the 5, 6a to the 5, bi plus dot, 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 right? There would be a whole bunch of terms. Solve this equal to 1, right? It'd be a huge pain. But with trig form, super, super simple, all right? Okay, so in general, our solutions, I should write down the general solution kind of in formula form for the 6 roots of unity. So this would be cosine. So again, the distance to the origin is 1, so I don't need the r term or the s term. So cosine of 2 pi k over 6 plus I sine 2 pi k over 6. All right, and oftentimes we don't even bother. So normally, right, I think it's a good habit to always cancel when you can. So here we have a 2 over the 6, so you can make that cancel away to 2 and make that into a 3. But in this circumstance, I think it's always a good idea to be able to see the 2 pi's, because the 2 pi is kind of the thing that makes it so that it repeats, right? So explicitly seeing that 2 pi, and also in a way explicitly seeing the 6 is really nice, because we're talking about the 6 roots of unity. So you can, easily identify that 6 with that 6 right there. So oftentimes I would just leave it like that. All right, in general, cosine, the solutions are going to be cosine. And you can imagine, right, if I have, I forgot to write down the problem, z to the n equals 1, the nth roots of unity, right? So this would be the nth roots of unity. Where would they be? Well, you would start at 1, and then you would rotate every 2 pi over n would give you another one, right? And if you rotate 2 pi over n, if you rotate that n times, you'll come back to where you started, and then any more rotations would just be repeating, right? So if we write down that idea, that would be cosine 2 pi k over n plus I sine 2 pi k over n. And here k equals 0, 1, all the way to n minus 1, right? Oh, I should write that here too, sorry, up here. K equals 0, 1, 2, 3, 4, 5. And the 6th one is the same as the 0th one, right? And same down here. The nth one would be the same as the 0th one. So altogether, there's n solutions. 0 to n minus 1 is n things, right? So there's going to be nth roots of unity, right? And they're all symmetric in this kind of in the same way that we've seen all the others being symmetric. All right, and again, the way I discussed this was just through the picture, but if you wanted to, you could do it all with algebra in exactly the same way we did the, for example, this one up here, this 4th root of unity example, right? This would be the algebra to go through it. But again, we've noticed at this point that there's asymmetries, and so we can just do it from the picture when we're comfortable with it. All right, so a good exercise for you right now is to just think, just draw out where are the 10th roots of unity, right? Just draw them. Okay, so let's now solve something more interesting. So let me solve something like z. Sorry. Before I do that, let me. No, okay, this is fine. Z cubed equals, let's say, 6 root 3 plus 6 I. Sorry. All right. Okay, solve. And we want to find all the solutions. All right. So there's going to be 3. Because again, this is a complex type problem, polynomial type problem, right? Z cubed. So there's going to be 3 solutions. So what we want to do is we want to write both sides in trig form. All right. So this one, the trig form of the right-hand side, is a little more complicated than what we have been doing, but it's still going to be the same process. So what we have is this right-hand side is going to be r cos theta plus I sine theta, right? Let me write it like this. 6 root 3 plus 6I is equal to this, right? Let's see. We said that our process for getting the trig forms, we get the R first, right? R should be the length, should be distance to the origin, and that should be the length of this the absolute value of this complex number, right? So R is equal to absolute value of 6 root 3 plus 6I, right? What is that? That's going to be 36 times 3 plus 36, okay? And so that's going to be, square root of that. And so that's just equal to square root 36 times 4, which is 6 times 2, which is 12. All right. Okay. So now in order to get the cosine theta and the I sine theta, we divide by 12 on both sides, right? So we know R is 12. So let me write that out. 6 root 3 plus 6I is equal to 12 cos theta plus I sine theta. And so that tells me divide by 12 on both sides. Root 3 over 2 plus 1/2 I is equal to cos theta plus I sine theta. Again, what we're doing here is we're figuring out this right-hand side, the trig form. All right. Okay, now that means we need to solve cosine theta equals root 3 over 2. Sine theta equals 1/2. We need both of them to be true, right? So for example, I want to emphasize that because, for example, here, cosine theta equals root 3 over 2. There's two solutions, right? So first of all, we're only interested in theta between 0 and 2 pi. So theta between, 0 and 2 pi. Because these are complex numbers, right? And so we're representing the complex numbers in terms of angles, and we only need our angles to be between 0 and 2 pi. If you go more than 2 pi, you're just kind of going a circle and then going a little bit more, right? So the circle part was unnecessary. Okay, so we're only looking between 0 and 2 pi. So cosine theta between 0 and 2 pi, how do you get root 3 over 2? Well, 60 degrees, right? Or pi over 3. And then there's the other solution, right? So right there, 60 degrees. And then the other one was 300 degrees, all right? Let me use radians. So pi over 3 and 2 pi minus pi over 3, right? Which is 5 pi over 3. Okay. So there's actually two solutions to this first equation here, but only one of these two is actually going to work for the second equation. All right. So which one works depends on this 1/2 here. If this was a minus 1/2, then 5 pi over 3 would be the one that we want, right? But if we just plug them in, sine pi over 3 is 1/2, but sine 5 pi over 3, right, sine looks like that, is actually minus 1/2. So that means pi over 3 is the one we want, all right, as opposed to 5 pi over 3. Okay, so what we conclude is r cos 6 root 3 plus 6I is equal to 12 cosine pi over 3 plus I sine pi over 3. Okay, because the other solution doesn't work. 5 pi over 3 doesn't fit with the sine. All right. Okay. Notice, however, if I had 6 root 3 minus 6I, then this would be a minus 1/2 here. And so the one that would work is instead 5 pi over 3. All right. And so that this in here would have been 5 pi over 3 instead. So you have to be very careful about these. All right. So what that means is ultimately we're solving for, we were solving for z to the 3 is equal to 6 root 3 plus 6I. So that translates into s cos alpha plus I sine alpha equals 12 cosine of pi over 3 plus I sine pi over 3. All right. Oh, sorry, cubed. All right. Okay, so what does that mean? Using deMoivre's theorem, we know that this guy down here on the left-hand side is s cubed cosine 3 alpha plus I sine 3 alpha. All right. And the right-hand side is still the same, cosine pi over 3 plus I sine pi over 3. All right. So immediately I know s is cube root of 12. All right. We can't simplify that anymore, so let's just leave it like that. Okay. And so we also know 3 alpha is pi over 3 plus 2 pi k, right? And there's the other solution where 3 alpha is equal to 5 pi over 3 plus 2 pi k. But that one's not going to fit with the sign. All right, just in this exact same explanation as what we gave up here for not fitting, right? So the other solution is never going to work, okay? So it's very straightforward. We just get this. And so alpha is equal to pi over 9 plus 2 pi k over 3. All right. All right. Oh, sorry. I should say what is k, right? K is equal to 0, 1, and 2. All right? Because again, we're dividing 2 pi k over 3. And so what happens is k equals 3 is going to repeat with k equals 0. K equals 4 is going to repeat with k equals 1, and so on. All right? So k equals only 0, 1, and 2. So that's exactly our 3 solutions. So if we write them out, our solutions are going to have angles. K equals 0 corresponds with alpha equals pi over 9. K equals 1 corresponds with alpha equals pi over 9 plus 2 pi over 3. And then k equals 2 corresponds to alpha equals pi over 9 plus 4 pi over 3. All right? Okay, why did I want to write this out? So that we can take a look at a picture. So alpha is pi over 9, right? What's pi over 9? The way we got pi over 9 was we divided our original angle, pi over 3, by 3, right? So the original, what I mean by original angle is the angle for the right-hand side, for this 6 root 3 plus 6i. Okay, so what happened was, if this was my angle, it was pi over 3, so 60 degrees. Right, so this was my 6 root 3 plus 6i. It was 60 degrees. Right, so what happens with my 3 solutions is I'm taking that 60 degrees, pi over 3, and I'm dividing by 3. That's actually 20 degrees, right? Pi over 9 is actually 20 degrees. So our solution is going to be, that's 1/3 of 60, so 1/3 of 60 gives me my first solution, k equals 0. Okay, so that's really nice in that our right-hand side was 60 degrees. To get my first solution, k equals 0, I divide that by 3, and I get my first solution. All right, where's my next solution, k equals 1? It's starting from my first solution, pi over 9, and then I add 2 pi over 3, right? What's 2 pi over 3? It's the full circle divided by 3, right? So that's 120 degrees. Right? But more importantly, it's the full circle divided by 3. So what I'm doing is I'm rotating now by 120 degrees, 120 degrees, and I'm getting to my second solution right there. All right? And then what's my next solution? It's the previous one, pi over 9 plus 2 pi over 3, and then plus another 2 pi over 3, which is another 120 degrees, right? So another 120 degrees. So that's going to be my third solution. And then if I go for k equals 3, that'll come back to my first one. All right. So what happens is I still have this same kind of symmetry that I saw before with the roots of unity, except the symmetry is slightly skewed, right? So I'm starting here instead of on the x-axis. But I'm still, once I start here, I go 120, 120, and then 120. All right. Just like with the roots of unity, I started here, 120, 120, 120. All right. So once I found in a way, Sorry about that. Once you find one solution, right, you just propagate by 120 degrees to get the next one. And again, the 120 degrees comes from the fact that we're searching for the cube roots. All right. So, for example, I can instantaneously solve some problems if I know. Let's say I want to solve for z to the fourth is equal to let's say 16 cosine of 20 degrees plus I sine 20 degrees, right? I actually know immediately the solution is going to be, I need to divide this guy by 4, right? So that's going to be 5 degrees. So that's going to be my base solution, my k equals 0 solution is going to be at 5 degrees. It's going to be a distance of the fourth root of 16 to the origin. So that's going to be a distance of 2. And then where is the next one? The next one is going to be 360 over 4 degrees away. So 90 degrees away. So next one is going to be there. The next one is going to be 90 degrees away from that one. And the next one is going to be 90 degrees away from that one. And if I go another 90 degrees, I'm going to start where I end up where I started. All right. So of course I can write down, if I want, all the degrees. If this is 5 degrees, then this one here is going to be a total of 95 degrees. This is going to be 185. That's going to be 275. And you can see it's just our roots of unity, right? Fourth roots of unity were here, 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 and here, except rotated in this direction by 5 degrees, right? To get that, and that instead, all right? So these roots of unity are very elegant in a way when you think about them in terms of complex numbers. And one more, I guess, aside, not aside, but one more comment. If I'm solving this, right, z squared is equal to, let's say, root 2 over 2 plus root 2 over 2i, right? So this is going to be 45 degrees right there, right? So I'm doing z squared, so that means I'm going to be at half of 45 degrees. So this is, let me do this in red here. So this is 45 degrees. So this guy here is going to be 45 over 2 degrees, 45 degrees over 2, right? And then that will give me my first core solution. It's going to be a distance of 1 from the origin, because root 2 over 2 plus root 2 over 2i, it has absolute value 1. And then where's the, probably should use different color here. So let me do this. Where's the second solution? It's going to be 360 over 2, which is 180 degrees away. It's going to be right there on the opposite side. All right. And if I go another 80 degrees, I'm going to come back to the first one. Okay. And again, this makes sense because whatever number this is, right there, my k equals 0 solution, this one on the opposite side is negative of that. And when I square the negative of that, of course, I'm going to get the same thing as the square of the original thing. So it makes sense that the other solution is right there. All right. So again, we have this symmetry as usual. All right. For the last thing in this section, let me kind of talk about a better way to write out trig form that actually fits extremely well with deMoivre's theorem. Well, first of all, it's more compact, easier to write, but also more importantly, it fits very well with deMoivre's theorem. So one problem with deMoivre's theorem, and all of this addition and multiplication and division of complex numbers, they're slightly complicated, right? You have to remember if I have z1 is equal to r1 cos theta 1 plus sine theta 2, sine theta 1, and z2 equals r2 cos theta 2 plus, I sine theta 1, of course, I sine theta 2, all right? Then z1, z2 is equal to r1, r2 cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. It's kind of complicated, right? Even just writing this down is kind of complicated. But there's actually a more compact way to express these. And that's actually, in a way, a third form of writing complex numbers. And it goes like this. So if z is equal to r cos theta, so we're going to use this up here. We're going to talk about that up here in a second. So we'll come back to that. Sine theta, right? then you can also write this as, so r stays the r, and then this is e to the I theta. All right, so e to the I theta is this guy in here. This is e to the I theta. This is called Euler's identity. I should write it by itself. So e to the I theta is equal to cos theta plus I sine theta. All right. So we're not going to talk about why this is true. That's a little bit beyond our class. But that's a very fundamental identity when it comes to working with complex numbers. And very frequently you want to write complex numbers instead of like this. In fact, you almost never use trig form in practice. You would always write it like this on the right hand side, because first of all, it's super compact, and second of all, it contains all the information right here. Cosine theta, I sine theta, they're kind of redundant because the theta is the important feature and the r is the important feature, whereas with the r e I theta, you see the r, you see the theta, you only have to write the theta once, right? Okay, so this is an identity that is true. All right, we're not going to discuss why or anything like that. If you take calculus after this, maybe middle of second semester calculus, you'll be able to understand that, because what happens is you can at least one way to see this, because you can expand cosine theta as an infinite polynomial. You can expand sine theta as an infinite polynomial, and you can expand e to the anything as an infinite polynomial. And if you do exactly all of that, they fit together perfectly to give you this guy here. All right, so that's just one way to see it. All right, in any case, I wanted to talk about this because this gives me a really nice and compact way to see deMoivre's theorem, or to remember deMoivre's theorem. In fact, I don't even have to remember it, because what is deMoivre's theorem? Or not even deMoivre's theorem, the multiplication and division properties of complex numbers. So what I mean is, see, we have the property up here, for example, the multiplication property that we just wrote down here, right? Kind of nasty, ugly, and we do have to remember, in a way, theta 1 has to add to theta 2. All right, theta 1 has to add to theta 2. R1 has to multiply to R2, right? And that's not necessarily so easy to remember. Maybe you remember it wrong and you add the R1 and R2, then you're in trouble, right? Maybe you remember it wrong and you multiply the theta 1 and theta 2, then you're in trouble. But if you use this REI theta form, you're not going to get into that trouble, because what happens is Z1 would be written as R1 e to the I theta 1. Z2 is written as R2 e to the I theta 2. Now what's Z1 times Z2? That would be R1 e I theta 1, R2 e I theta 2 times that, right? But this is just regular multiplication. So R1, R2, so that's just R1 times R2. Right? And that gives you exactly this R1, R2 up there in the expression upstairs. All right? So I didn't have to remember, because when I wrote this down, this is literally R1 times e to the I theta 1 times R2 times e to the I theta 2. So of course, it's equal to R1 times R2. And then what about the next one? The e's. This is e to the I theta 1 times e to the I theta 2. But they're both e to the something. So using the properties of powers, this becomes R1, R2, e to the I theta 1 plus I theta 2. All right? But I have an I on both of them, so I can factor it out, e to the I theta 1 plus theta 2. All right? So just using properties of powers, particularly right there, from here to here, right? We see that we get exactly this property that we, in a way, had to memorize previously, instantaneously, without having to think about or try to remember what the properties were. All right. So this is a really, really nice way to express complex numbers and to work with complex numbers, right? My memorization is reduced to zero, is reduced to understanding properties of powers. But that's something that we should always know anyway, right? So in essence, our memorization is reduced to zero, okay? In the exact same way, Z1 over Z2 is R1 e to the I theta 1 over R2 e to the I theta 2. That's equal to R1 over R2, right? Remember that when we divide, we have to divide the R's, the distances to the origin. ei theta 1 over ei theta 2, that's e to the I theta 1 times e to the minus I theta 2. Because 1 over something is that something to the minus power, right? Okay, but this is equal to r1 over r2, e to the I theta 1 minus theta I theta 2, which is equal to r1 over r2, e to the I theta 1 minus theta 2, right? And remember, when you do divide, what we talked about previously was we had to memorize. It was r1 over r2, cosine theta 1 minus theta 2, plus I sine theta 1 minus theta 2. Right? But here it just pops out automatically using properties of powers. Again, the same property of power to combine these two guys, and the property of power to make this guy in the denominator into e to the minus I theta 2. All right. Okay, and finally, deMoivre, z to the n, right? This is going to be r e I theta to the n. What's that? Well, we're just multiplying two things. So whenever you have the product of two things to the n, that's equal to the first thing to the n times the second thing to the n, right? But here, properties of powers, when I have e to the I theta and then to the n, that's the same as e to the I theta times n, right? And let me rewrite that order. That's e I n theta. Okay. So what's happened? We've rotated the angle by a factor of n. And that's exactly deMoivre's theorem, right? Let me actually write that down just for reference. Z to the n is equal to r to the n cosine n theta plus I sine n theta. All right. So again, the whole point here is you don't have to memorize anything. You just have to know, let's see, this property of powers that goes from here to here, which again, you absolutely should already know, right? So in essence, there's no extra memorization involved here. All right, so in practice, again, this is how you work with complex numbers when you need them in some sort of trigonometric form. You don't actually, almost nobody writes out, literally probably nobody use the cosine and then the I sine. They would always just write the r e I theta instead, because it's just so much more compact. And also, so this is where, I don't know if you've seen this in the past, e to the pi I would be equal to minus 1, right? Because e to the pi I represents cosine of pi plus I sine of pi. Cosine of pi is -1, sine of pi is 0, so this is equal to minus 1, right? So e to the, this is kind of a fun expression that you'll sometimes see math nerds talk about because it looks weird, right? -1 is equal to this crazy expression here, but it makes complete sense when you talk about, even when you talk about it in terms of trig form, right? Cosine pi, I sine pi is exactly -1. All right, but that was just for fun.